Hello.
Yeah.
I thank IAVM for giving one more opportunity to discuss related to my work in graph theory applications found in ancient Indian scripts. We have conducted the third international conference. It was very successful, and I'm participating in so many presentations in different institutions to create awareness related to Vedic mathematics, and particularly awareness related to applications of Vedic mathematics in digital systems. You can see so many presentations have been given. I am very much fortunate that I am very much associated with IAVM and guided by IAVM to discuss these things, as well as to promote Vedic mathematics in the different institutions in India. Coming back to my presentation, so this presentation is having graph with the title Graph Theory Applications Found in Ancient Indian Scripts. The abstract of the webinar is this way. This webinar is focused on the investigation of shlokas in the ancient Indian scripts, which discusses the concepts of graph theory as applied by Sanskrit poets in composing verses and interesting unique problems related to chess. So this involves three different concepts. One is shlokas in ancient Indian scripts. The other one is the concentration on graph theory concepts, and one more thing, chess related problems here. So I am going to discuss about graph theory concepts also, whichever is relevant for this presentation, and then related to Sanskrit poets who have done great work in writing shlokas, and also which relates to graph theory, as well as what are the problems related to chess, and which is helpful for computer science also, and then combining together what works have been done, what shlokas we are going to explore, one or two I am going to discuss in the today's webinar. Coming to the concept of graph theory. So if we observe any problem, whenever you want to solve any real-time problems, first we are going to write graphs, because graph is going to represent, or graphical representation is going to give lot of information. So a graph graphs are a structure for describing relationships between the objects. Objects we can consider, let us say you take an example of, you take first example is personal assignment problem. Timetable problem when you are going to take for teaching schools and colleges also, assigning people to different jobs, arranging weddings and all these. Social network problem in the computer network, as well as transportation, road maps and connecting the systems, as well as electrical systems, VLSI design and geometric polyhedra, and in chemistry, biology, ecosystems, and scheduling the timetable problems and puzzles. There are lot many examples are there where the concepts of graph theory is used. Now today we are going to just explore a bit which is relevant, the concepts of graph theory, which is very much relevant to our topic related to shlokas. When we hear graph theory, immediately it comes to our mind Königsberg bridge problem. So just a small explanation about the Königsberg bridge problem. So you can observe there are three land spaces are there here. They are connected by 7 bridges. That red colors are the bridges are there. 1, 2, 3, 4, 5, 6, 7. These 7 bridges are there. People used to pose a problem. Is there a way to cross all 7 bridges exactly once and return to your starting point? So to solve this problem, so what we have to practically do, you start from one space, then cross each of the bridges and come back and try out into different ways. For that, in 1736, Euler came up with a solution how to solve this problem. He has presented the land spaces by vertices. You can see A, B, C, D are the vertices which are represented as the land, and the bridges are represented by the edges here. So from land space A to C to A, there are 2 bridges are there, which is represented as CA is one edge and C 2 edges, one is through C, another one is through D. Like that it is going to represent. And this, for this problem, great Swiss mathematician Euler solved the problem, the 7 bridges of Königsberg. He represented this in the form of a graph, and you can observe that each of the vertices you observe, The vertex we call in mathematical, in the graph theory notation, the degree of a vertex. What is the degree of the vertex? The number of edges which are incident with a vertex is called as a degree, we call. You observe, let us say go to the vertex A. Vertex A is connected to 1, 2, 3, 4, 5 edges are connected. Similarly, C is connected to 3 edges, D is having 3 edges, and B is having 3 edges. So degree of each of the vertices is odd. So hence, whenever you pose a problem which are having the vertices of degree is equal to 5, it is not possible to start from one vertex and go through all the edges exactly once and come back to this one here. This was the solution given by Euler, and any graph we are going to call Euler graph or the Euler graph, we call if each of the vertices is having even degree, that means each of the vertices are connected through minimum even number of edges are there, like 0, 2, 4, 6, 8, then only it is possible to solve some problems related to starting from one point, going through all the edges exactly once and come back to same point here. So this is usually in any of the engineering institutions, or whenever we think of concept of graph theory, we immediately connect it to the problem of Königsberg bridge problem. Coming to Hamiltonian cycle, we are going to call. I am directly going into the concept of Hamiltonian cycle because it is directly related to our topic. We have Hamiltonian path. Hamiltonian path means it's a path that visits each vertex exactly once. Let us come back to this Königsberg bridge. Assume that I am going to start from C. When you start from C, I'll go to A either through the bridge C or I can go through the bridge D like this here. In case of Euler graph, I have to cover all the edges is a importance here. In case of Hamiltonian path, it is I have to touch each of the vertices exactly once. This is the difference between Euler graph as well as the Hamiltonian path here. Hamiltonian cycle is what? I'll start from one vertex. I'll go through all the vertices exactly once and come back to the same vertex. It is not necessary that I have to go through all the edges here. So we are going to form a Hamiltonian cycle. A graph that contains a Hamiltonian path is called as a traceable graph. A graph that contains a Hamiltonian cycle is called as a Hamiltonian graph. A simple example I'll just show you. So this is a dodecahedron represented in the form of in the plane figure. It is represented here. So we have to find out the Hamiltonian cycle, means our interest is start from one vertex, go through all the vertices exactly once and come back to the same vertex. It is not necessary that we have to cover all the edges here. So one simple solution is given. You can start the diagrams, the arrows are here. You can start from the topmost vertex, come to right side here. So this is red. All the directions are shown here. You can move like this, and through all these you can directly move here, and you can come back like this, and you can go back to the initial vertex. This is one such Hamiltonian cycle here. Just to understand what is a Hamiltonian cycle, there may be different Hamiltonian cycles for a given graph also. So this is some basics related to the graph theory which is of our interest, where particularly the Hamiltonian cycles which is of our interest in our discussion today. So this is related to graph theory. Now coming to Sanskrit shlokas. When we discuss about the Sanskrit shlokas, we call kavyas, we are going to call. This is Sanskrit poetry has incredibly vast variety of forms and structures. At the top we have got what is called as Mahakavya in classic style, narrating a noble story element satisfying all the norms and principles prescribed by the Alankara Shastra text. So this is also called as Uttama or superior Kavya. The intention of a poet in such Kavyas, which is called as Uttama Kavya or which is the Mahakavya, is to communicate the mental states of characters to the reader. This is one. And the next one we have, there are other varieties are also there. There are varieties of slightly less elaborate kavyas, Laghu Kavya, Champu Kavya, Giti Kavya, Muktas, biographical poems, anthologies, and stotras. Among these is a magnificent class of verse based in adaptable play of vowels, consonants, words, and also sounds. In these shlokas, the poet is going to play with vowels, consonants, and all, and he is going to obtain different types of poems also it is possible. The components of the poetry are now and again pleasantly patterned into some designs which we call it as bandha. A geometric figures are along with picture of usual things in life. For example, a blossom, a wheel, it represents a drum, or it may represent an umbrella, mace, and so on. The poet is going to play in a way such that it is going to represent different designs also. Coming to Chitrakavya, so the name Chitrakavya has come because maybe as a result of its pictorial quality, it represents some picture. This class of poetry is also known as Chitrakavya. The intention of the poet composing Chitrakavya is to exhibit his skills in handling language amidst several constraints are there. One such constraint we are going to take up in the discussions today. So Chitrakavya is also referred to as Adhamakavya, or it is the inferior we are going to call. The object of Chitrakavya is to incinerate admiration and wonder, to evoke amusement and pleasure, and to offer intellectual challenges is the intention of this. The Chitrakavya aims to create a feeling of wonder by resorting to unusual management of certain meters. Innovative poetic structures, designs or patterns called as bandha, resembling objects or their movements, which is called as gati we are going to call, that one commonly sees in everyday life. Chitrakavya can be treated as architecture of poetry where the sounds of syllables and letters take a visible form. That's why Chitra, or we are going to have a diagrammatic representation also. Our Sanskrit poets have done a lot of work in this. The playful indulgence of Chitrakavya techniques were used by major poets such as Kalidasa in Raghuvamsha, Kumaradasa in Janaki Harana, Bharavi Kiratarjuniya, Magha Shishupalavada, Ratnakara Haravijaya, Vedanta Desikar Paduka Sahasram. Some examples we can take: the movement based figurative poetry, which is Gati Chitra. Gati means movement, such as Gomutrika, which represents a web-like structure. Jalabandha Anuloma Pratiloma, which looks like a palindrome. Sarvato Badra, Ardha Brahmana, like when you go halfway, again you turn backside and come back here. Turaga Padapatha, Ratha Padapatha, which represents chariot movement. Gaja Padapatha, which represents the elephant movement, are abundantly used by many of our poets. These are some simple examples are there. The first one is it represents a musical drum pattern, and the second one it is representing Ardha Brahmana. You can see when you take the movement here, will not go up to all the 8 squares. Like if you take 8 by 8 squares, we are going to only half of that we are going to move like this, which is Ardha Brahmana. Next one is Gomutrika, which resembles World Wide Web, the connections like this. For a computer science student, there are so many problems are there, as well as those who play chess. N-Queen's problem, Rook polynomial, and as well as the Knight's Tour problem are a very challenging problems, and writing a program so that we are going to play with queens or rooks or the knight problem are very interesting problems in computer science. Coming to the Knight's Tour problem, which is relevant to our presentation. What is Knight's Tour problem? The Knight's Tour problem is the mathematical problem of finding a Knight's Tour. Creating a program to find a Knight's Tour is a common problem given to a computer science student. There are variations of the Knight's Tour. The variations of Knight's Tour problem involves chessboard of different sizes than the usual, like 8 by 8 directly. This is usual Knight's Tour problem, as well as irregular, which is we can have not only 8 by 8, we can have 5 by 5 or 4 by 8, 4 by 12, 4 by 16, such problems also, where we have to find out the Knight's Tour problem. So what is this Knight's Tour problem? The knight is placed on an empty chessboard. Only the knight is going to move, and it follows the rules of chess, like how the knight is moved, and it must visit each square exactly once. This is where we are going to come across what we have studied, Hamiltonian cycle also. In case of Hamiltonian cycle, what has happened? Our interest is to start from one vertex, go through all the vertices exactly once and come back. This is the Hamiltonian cycle, or Hamiltonian path means it is not that we are going to come back to the same vertex to other vertices. Only thing is we are going to cover all the vertices there. It is similar to here in case of chess. If you take either a 8x8 chessboard or maybe 4x4 chessboard or 5x5 chessboard, I am going to place the knight at one position, and it has to follow the rules of how the knight is going to move, and then it has to go through all the blocks here and exactly once, and it has to cover all this. This is the problem. So there are several billion solutions to the problem, of which there are 12 crores of such knight finishing on a square which is just a move away from the starting square. We can look into this knight tour problem. A chessboard with odd number of squares has no tour at all, because the knight's graph is a bipartite graph also. What is called as a bipartite graph is, we take a graph. The graph consists of vertices as well as the edges. I am going to split the vertex set into two subsets, that is V1 and V2. I am going to merge these two. V1 union V2 is equal to the set V, and V1 intersection V2 is a null set. So every edge, if it is represented as an edge from one vertex in one set to the one vertex in another set, then this is called as a bipartite graph. So for the knight's tour problem, it represents a bipartite graph. Only the bipartite graphs with an even number of vertices can have a Hamiltonian cycle. Now let us look into one small demonstration of how an 8x8 problem can be solved here. So many people have written some programs also related to solving the problems in 8x8. I'll show you a program which is written in C, C++, Java also it is written. There are many ways are there. One is either you are going to place the knight at a position, this position, like I am going to show you, this is 0. Then take the knight movement, it is equal to, it goes to 1, then it goes to 2. It covers all the blocks in the 8x8 chessboard. In this program, what is going to happen? You are going to start from the left corner itself. There is another program also where you are going to place the knight from any place inside the chessboard, whether it is a 8x8 chessboard or it may be a 12x12 chessboard also. You can observe, I have just executed one program which is already available. So you can observe that in the first row itself, that is 59, 14, 63, 32, 1 is there. From here it has started. In the next run, see here, you can see the black space here. So it starts from last but one row, it is going to start from here, then it goes like this. As you go on running this, you are going to get different initial positions also, and you can have many different solutions which are possible for this here. So all of them are going to give the solutions of how the knight movement can be done. It becomes a combinatorial problems. There are a number of solutions for a given chessboard itself. Coming back here, so it is not that always we are going to work with the n by n chessboard itself. There are some problems also there, which is knight's tour problem of 4x8, 4x6, 4x12, and all these are there. One simple solution we can just observe here for this one here. So this is a 4x8 chessboard. You can just observe all the movements of the knight is recorded here, so that it is going to follow the rules of the chessboard, as well as it is going to cover all the blocks which are available in the chess without repeating anything also. So this poses a very, very interesting problem in solving some problems related to chess, as well as writing a program so that it is going to follow the rules of this. Now, clubbing all these together, now let us look into what we are interested in. Now we can observe this also, this for the knight's tour problem. So we have 4x3, 4x4, 4x6, 4x8, and all these things. There are many solutions are also available. This table is taken from a paper written by Avani Kumar, Studies in Tours of Knight on Rectangular Boards also. So out of these, we are very much interested in 4x8, that is 4 rows and 4x8 chessboard, and we are going to explore something here. Now coming to this of our interest. One is, I already told you, Paduka Sahasram, which is written by Vedanta Desikan. In the 12th century itself, it was written here. I'll just read out this shloka. This is the first verse. Sthira, it is written like this. Sthira gasam sadaradhya vihata katata mata satpaduke sarasama rangaraja padamnaya. The English version also I am going to just show you and also share it with you. So what we are going to do in this case here, or what the author has done in this here, he has taken, this shloka is consisting of 32 letters here. So each of these letters, it is placed in the half of the chessboard, because 32, there are 4 rows, we are going to place it here. So you can observe here, Sthi, it is placed in the position A8, and Ra, it is placed in B8. Then go on like this, Gasam, that is C8, D8, and Sadaradhya, this line is over. Next, coming to the next line here, Vihata katata mata, Vihata katata mata Satpaduke sarasama, Rangaraja padamnaya. So here, if we are going to place this here, now let us take the movement of night in this here. So here, if you start from the position A8, that is Sthi, I am going to start with this. We can have the movements of the night in different ways here. I can go to the position here where it is C7 also. I can go to the position like B6 also, I can go like this. But all of them are not going to give a solution for us. Some of them, if we are going to pick the letters which are there and merge together, it may result into some shlokas which can give a different meaning also. So therefore it is a combinatoric problems also. So when you take this example, let us say I am going to move, that is the night movements are also mentioned here. Initially I am going to start from the position A8 here, which is Sthi, and I can move to either this position C7 or I can move to the position B6 also. But in this case, I'll move to the position C7. So this is Ta. So you take this letter here. Now you form one more shloka, Sthi. Then you are going to have Ta. From that you can also move to different position also. But let us follow this here. From here you move to the position E8. From here we are going to move to the position E8, which leads to Sa. So wherever my night is moving there, I will pick those letters and I am going to place it here. This has come to Sa. Next, from this position you go to the position G7. So this is G7, Sa Ma. So like this, as it is mentioned in A8, C7, E8, G7, H5, F6, D5 and all these, when you move in this direction, definitely it is going to cover all the blocks in the half chessboard, and wherever it is ending in that particular letter, pick those letters and place it in another shloka like this. So this forms another second verse which is written by Vedanta Desikan. So this gives Sthita Samaya Rajatpagatara Madake Gavi Duram Hasam Sannatada Sadhyatapaka Rasara. So this has resulted into another shloka also. The explanation of these two shlokas are given by the author here. The meaning of first verse is, it is both praying to, both of them is going to give the meaning, it is prayer to his God. O the sacred Padukas, that is the feet of Brahman, you are adorned by those who have committed unpardonable sins. You remove all that is sorrowful and unwanted. You create a musical sound and lead me to the feet of Lord Rangaraja. This is the meaning of the first shloka here. When you are going to take the night's tour of that and whatever the next shloka we are going to come across, this is having a meaning. The Padukas which protect those who shine by their right attitude, who is the origin of the blissful rays, which destroy the melancholy of the distressed, whose radiance brings peace to those who take refuge in them, which move everywhere. May those golden and radiating Padukas of Brahman lead me to the feet of Lord Rangaraja. So he prays to Lord Rangaraja with these, and we can observe that. So he has played with the letters also, as well as how much of interest in, if you are going to take, if you place these into chessboard also, it is going to give one more shloka also. So the second verse is not only provided the solution to the knight's tour problem, but went far beyond that. It is said composing such verse is far more difficult than solving the original chess knight problem, because it is a combinatoric problems also. Out of this, if I am going to take the letters which where the knight is going to move, and I am going to form one more shloka, there are different ways are possible. Out of that, it has to give a good meaning, as well as it has to satisfy the condition of how the shlokas are written in the Sanskrit also. Definitely it was a challenging problem which is solved by him. Similarly, we have surveyed and we have come across one more shloka like this in Kavya Lankara. It is the following verse by Rudrata was the earliest example in which the moves will give the same verse itself. In the previous case, what has happened? It has given a different verse. Now in this case, it is going to give the same verse itself. I am going to just read out this shloka. Sena li 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 na na li li na 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 li 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 nali nali le nali na li 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 na 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 nali. So we place this in again the same way in the half chessboard itself. Again you see the movement of this the knight here. We start from A8 here, that is say, then C7. When you go to C7, again it becomes na. From there you move to E8 li. When you go in this movement also, so in the previous case we obtained one shloka. In this case we are going to obtain the same shloka itself. This is another thing which was done by Rudrata. When you go through this also, let us have a comparison of these two. In the first one, what we have seen here in the first shloka there, it follows the same thing here: A8, C7, E8, G7, H5, F6 like this up to A7. And from here in the second line also, only the deviation is in the last three positions of the knight here. In the C5, A6, B8. In case of the second shloka, it is B8, A6 and C5 here. If you observe the first pattern, that is the first line in each of them, they are common here. And also I have taken the snapshot of this half chessboard when we are going to go through only the 16 letters which are there in the shloka here. You observe that there is a pattern is also possible here. So this opens up another interesting thinking, like if we are going to come across like 16 line shlokas or 32 line shlokas, if we try to place the shloka or each of the letters in the half of the chessboard here, and if you are able to follow the same pattern here, so definitely it may lead into some other different thinking also, or it may give another shloka. So many things are also possible here. So this pattern is repeated in each of them. Only the last line, in the last three places only the deviations are going to occur in the second shloka itself. Similarly, there is another one word which is called as the Jalabandha, which is called as the web we are going to have here. In this verse, what has happened here? You observe the second column, fourth column, sixth column, as well as the eighth column here. When you observe all these, thus each of the even numbered columns are having the same letters here. This is having da, and this is having ja, and another one is having she, and also taha. And you can start, the poet has played with letters in a way such that you can start, either you can read the shloka in the straight line like this, or you can also start here like sa, come to the second row, second letter, again go up, come here like this. This is some movement you are going to come across. Or you can also come from here, go to the third row, second letter, again you can move in a different direction like this. So these are and you can just observe, you take out all these letters and you can observe what is called as a K44 graph, which is called as a complete bipartite graph also you are able to observe from this. So we can also conclude from some of these things. So this presentation makes a novel attempt to bring together the disciplines of graph theory and Sanskrit poetry, that is poetics, by analyzing certain types of pattern poetry, which is called as Chitrakavya, using the principles of graph theory. Though Sanskrit poets are far removed from us on time scale, the verses composed by them exhibit some similarity with the concepts dealt by graph theory, which one simple example we have seen. In addition to the various applications of graph theory in modern disciplines, we could summarize that it is also useful in composing particular forms of constrained poetry. What is the constrained poetry here is we have to take only the movement of the horse itself and we have to cover all the places also. This is some constraint is there. In that there are n number of solutions, but in such n number of solutions, one such solution is going to give a good meaning or it may get back another shloka also. So this does not, however, imply that Sanskrit poets were aware of graph theory, but only that Chitrakavya verses that they composed are compatible with graph theory and can be studied in the latest background. So I want to acknowledge Dr. Shankar Rajaraman. He is a doctor by profession. He is also a PhD scholar in Indian Institute of Science, Bangalore, who has guided us to contribute for this work. And these are the references I have taken on Balasubramaniam, which is Chitram, and King Bhoja's work, Mahaga's work, and Shankar Ramanujan himself, he has written a book, and Chitrabandha also, he has written some books also. This is a small insight into the graph theory concepts which can be observed in the Sanskrit shlokas, as well as some problems, which is the night store problem, which is a very interesting, as well as a combinatorics problem, where it is really a challenging problem for the mathematicians also, and to dig deep into the shlokas, which can give different insights into mathematical puzzles as well as the problems which are there available in our Sanskrit shlokas. So thank you very much for giving me an opportunity to discuss related to these things. Thank you, madam, and thank you, sir. Thank you for your patient listening.